My favorite Skittles are red. What's the probability that if I randomly squeeze 5 Skittles out of this bag, that there'll be at least 2 red? Let's give it a try. So here we go. It's 1, 2, 3, 4, 5. There was only 1 red out of 5. So let's think about that. Is that a binomial situation? Okay, so here's it. If I take out 5 Skittles, how likely is it? Well, 2 will be red. Well, I got 1 red. Let's think about this. Is this a binomial situation? Well, we do have red or not red. How about independence? Well, we're sampling without replacement. But if you think about the fact that Skittles are made in enormous batches in a factory and then they're put in these bags, I would say my 5 Skittles is certainly less than the 10% of the Skittles population that went into making this bag. So I think we're good for independence. My n is equal to 5, and now the probability. Is there a fixed probability of getting a red every time? Well, it turns out there is. It turns out that we have a 20% of each color, so we can say then that the probability for the success probability is equal to 0.2. So probability of getting red. So all of our conditions are met, so we can use the binomial model to answer this question. How likely is it that 2 of them will be red? So the probability that x is equal to 2 is going to be a binomial model, a binomial distribution with n equals 5 and p equals 0.2. So this is going to be 5 select 2, 0.2 squared times 0.8 to the third. And that turns out to be, I need to check my notes here for this, that turns out to be 0.2048. So there's only a 20% chance that I would have gotten 2 reds out of 5. Now the second question is, how many Skittles do I have to draw out of the bag on average until I get the first one? So how is this different than the other one? So I'm back with my Skittles bag again, and I'm going to start pushing those Skittles out of my bag here, and I'm going to see how long it takes for me to get my first red one. I got 1. Oh, that was a yellow. It kind of escaped on me there. Let's get it back here. There's 1, there's a yellow, then there's a purple, so that's 2. There's another yellow. They keep rolling away. 4. It took me 4 to get my first red. Okay, so let me try it again. See what would happen next time. I'm not even sure if there's any red left in this bag because I've eaten a lot of these, but let's just check it out. 1, 2, 3, 4. Oh, it took 4 again. So if we did this lots and lots of times, which we did in class, we would find out that sometimes we would get a red on the first try, sometimes on the second try. Sometimes it took 23 or 24 tries to get our first red. So let's see what that looks like when we graph that. And I've got this on here. Let's see here. That wasn't it. Here's our class data. Let me remove that here. This is our class data. So we saw that a couple times we got it on the first try, a bunch of times we got it on the second try or the third try. So the majority of the time, it looks like we got our first red Skittle between 1 and 9 tries. And then there were a couple times where it took 13 or 15 or even 23 or 24 tries before we got our first red Skittle. So what kind of a distribution is this? Let's think about the probability of this. What's the probability of picking the first red Skittles on the first try? Well, that's just a 0.2 probability because we have a 20% chance of getting a red Skittle. So what's the probability that we got it on the second try? Well, that means we didn't get it on the first try, so there's a 0.8 of not getting the red Skittle, and then we did get the red Skittle, and since they're independent events based on the 10% rule, we can multiply those probabilities. So that's 0.16. The probability of getting the Skittles on the third try then would be 0.8 times 0.8, 2 failures times a success, and that turns out to be 0.128. So you notice it's getting a little less likely each time. What's the probability that of getting my first Skittle on the fourth try? Okay, so I have 0.8 to the third times 0.2, which turns out to be 0.1024. On the 10th try, well, that would be 9 failures, so 0.8 to the 9th times 1 success, and that would give me 0.0268. So we could generalize this and say if we made, what's the probability of getting the first red Skittle on the xth try? Well, that would mean we would have x minus 1 failures, and then on the last time, that would be our success. So you notice what's happening to these probabilities. They're getting smaller because each time we're multiplying by a number less than 1. We're multiplying by 0.8 over and over and over again. So the probability is decreasing as x increases. Now, you might recall that this formula looks a little bit familiar. Let's think of our a sub n equals a sub 1 times r to the n minus 1. Our success would be this, and then we keep multiplying by this each time. This is a geometric sequence. So it actually forms a geometric sequence. And if I were to go on my calculator, I can show you this. Let's see, where did I put this? Okay. I went ahead and looked at the number, put the number of trials in this column, and then the probability of getting the probability of that. And the way I did that was I took 0.8 raised to the power of the number of trials minus 1. That would be our x minus 1, and then times the success. So we have this many failures times the success. So when I got my first success on the first trial, that would be 0.8 to the 1 minus 1, 0.8 to the 0 times 0.2. So this is what we got. And then I made a graph of this, which is over here somewhere. Okay, there's the graph. Notice this looks like a decreasing exponential function on the top edge, and that's what a geometric model will look like. These are the probabilities that keep decreasing. Each probability is 0.8 of the previous times the previous probability. Now, does this keep going on? Well, let's look. I put in, let's see here. If I go down here, I did this down to 25, I think. Yeah, 26, 27, 28. Okay, I did some more. I did up down to 30. Okay, well, what if I put in 31? Is there still a probability associated with that? Yep, 32, 33. It's getting pretty small, but what turns out is this is never going to end. This is going to go, this is infinitely. So theoretically, I could draw an infinite number of Skittles before I get my first red. Now, the probability of that's going to get smaller and smaller and smaller and closer to 0. But it's never going to actually equal 0. So if I added up an infinite number of probabilities, I would get a sum of 1. But we can't ever really make a table out of this because there are an infinite number of possible trials, theoretically. Probably I wouldn't be drawing an infinite number of Skittles from my bag because the bag wouldn't have an infinite number, and I would get really tired of doing it very shortly. Okay. So let's examine this geometric model. The geometric model answers the question, what's the probability of getting the first success on the xth trial, where x equals the number of trials until I get the first success, which in this case was a red M&M. Oh, sorry, red Skittles, not M&M. I like M&Ms too. If we look at the conditions, there's still only 2 possible outcomes, success and failure, red or not red. Trials must be independent. We invoked the 10% condition for this to say that they were independent or that they could be considered independent. And the probability of this success is the same for each trial. That is true. We have a 0.2 chance of getting a red M&M on any one draw, but the difference is the number of trials is not fixed. So we don't have a fixed number of trials. That's what makes this one different from the binomial. In this situation, our probability of success is still called p, and in this example was 0.2. Our probability of failure is 1 minus p, which is also known as q lots of times in symbols, and that's 0.8. Our formula for finding probability is going to be then the probability of failure which is 1 minus p, to the x minus 1 times the probability of success. In this case, it's 0.8 to the x minus 1 times 0.2. Now, what is the mean? Let's go back and look at our graph, which I keep flicking back and forth to. So what does the mean look like? It's very heavily skewed to the right, so that's a difficult thing to tell. What do you think the average is? Okay, students guessed anywhere from like 4 to 7 or 8, and they said that, you know, they were kind of thinking around in here somewhere. So what is the mean? The mean, it turns out, is 1 divided by the probability. So in this case, that would be 1 divided by 0.2, or 1 over 1/5, which is 5. And that really makes logical sense, because that's saying if there is a 1 out of 5 chance of getting a red, on average it's going to take me 5 tries to get a red. So on average, I will need to draw 5 Skittles in order to get my first red. Now, what's the probability of getting your favorite color on the second try? We already did this. I'm not really sure why I put this problem here. So the probability that x equals 2 is going to be 1 failure times 1 success, or 0.16. What's the probability of getting your favorite color on the second or third try? Well, that's the probability that x equals 2 or 3. Well, we just add the probabilities. So we have 0.8 times 0.2 plus 0.8 squared times 0.2 for the third try. And that turns out to be 0.16 plus 0.128, or a sum of 0.288. So there's about a 28% chance, 29% chance of getting my favorite color on the second or third try. What's the probability that you do not get your favorite color until after the 5th try? Now this one's a little trickier. It means that we have 5 tries where we don't get a red, and then after that we get a red sometime. But it doesn't say on which one, it just says after that sometime. So one thing I can do is think about, I know that I could add up all the probabilities of getting a red on the first or second or third or fourth or 5th try, and then just subtract that from 1 to see what would be anything other than that. So I could do 1 minus the probability that x equals 1 or 2 or 3 or 4 or 5. So that would be 1 minus, and then I could do all these probabilities. 0.2 plus 0.8 times 0.2 plus 0.8 squared times 0.2 plus 0.8 cubed times 0.2 plus 0.8 to the 4th times 0.2. And by now you're saying, surely, Mrs. Taylor, there is a simpler way to do this. Well, there is a little formula, there is a little gizmo in the calculator that can do this. This is one way to do it. Another way would be to do 1 minus the geometric CDF on your calculator. And you only have one parameter, is the probability, and then you're going to be going from 1 to 5. So let me show you what this looks like when you do this on the calculator. So let's insert a calculator page, and we're going to do, I'm going to go ahead and do the 1 minus, and then we go to our menu, we go to statistics and our distributions again, and once again these are just below the binomial, so geometric CDF, the probability of success is 0.2, and we're doing trials 1 through 5, and that would be our value. But there's another way, so that's 0.32768. I'll go ahead and put that down, 0.32768. But there's actually an easier way to do this. What is the probability that I do not get my favorite color until after the 5th try? It's the probability that the first 5 are not red. So this is just the same as saying 0.8 to the 5th. Double check this. 0.8 to the 5th. Bingo, same thing. That's a lot easier. But in the heat of an AP test, you may or may not just think about which one you would do. They actually turn out to be exactly the same thing. So you kind of think about that and why that makes sense. Well, that's it for the geometric model. It's a pretty simple one. I usually do not use the formula for this. I usually just think about it as how many failures in a row times one success. That's usually the easiest way for me to think about this. And we are done. Oh, by the way, we are not doing, I'm skipping over the normal approximation to the binomial right now, so this is the end of our 6.3 notes.